All right, let's dive in. Today we're exploring the intersection of machine learning and climate modeling.
Sounds complex.
It is,
Mm.
but also fascinating. Specifically, we're looking at DYffusion and SFNO.
Okay, and for our listeners who are machine learning experts, why should they care about this?
Great question. They should care because these techniques are being used to tackle climate modeling, which has unique challenges.
Right. See, machine learning has revolutionized weather forecasting, short-term stuff, but climate modeling, different beast.
Completely. We're talking about simulating Earth's climate over centuries, way beyond just tomorrow's weather.
Exactly. Long-term stability, accuracy, physical consistency over immense timescales. That's what we need.
So not just will it rain tomorrow, but how will rainfall patterns shift over the next 100 years? Tricky stuff.
Think of it like this. Predicting a ball's path for a few seconds, easy. Predicting where it lands after an hour of bouncing, much harder.
Perfect analogy.
Yeah.
And that's where DYffusion and SFNO come in,
Yeah,
right?
exactly. We've got this paper, Probabilistic Emulation of a Global Climate Model with Spherical DYffusion. It really digs into these techniques.
And one key takeaway that struck me is just throwing more ML power at climate modeling doesn't guarantee good long-term projections.
It's true. The paper even has this visual comparing the weather forecasting skill of different ML models to their climate performance. And surprise, models that ace short-term weather predictions don't necessarily translate to accurate long-term climate simulations. So, different ballgame.
Now, the paper introduces spherical DYffusion, combining DYffusion, a diffusion-based forecasting framework, with SFNO.
Ah, yes. SFNO, the spherical Fourier neural operator. A mouthful, but powerful for modeling global data, Earth stuff.
Right, because understanding how, say, ocean currents in one place can impact weather patterns across the globe, that's crucial for climate modeling.
Exactly. SFNO excels at capturing those long-range interactions and global patterns.
Okay, so we've got DYffusion and SFNO working together in this spherical DYffusion thing. Can you walk us through how it actually generates these climate simulations?
Sure. So you start with, say, today's weather conditions, and you want to predict, let's say, a few steps ahead. Now, DYffusion, it's a bit different. Instead of directly predicting future weather, it imagines a process where the weather gets more and more random.
Like adding noise to a photo, eventually making it unrecognizable.
Precisely. But here's the twist. DYffusion trains a machine learning model to reverse this process, to denoise the weather and recover the actual future conditions.
Okay, so it's trained to undo the randomness and find its way back to the real weather patterns. Pretty cool. But where does SFNO fit into all this?
That's where the spherical part comes in. SFNO is all about modeling data on a sphere, our planet's shape. It uses the spherical harmonic transform, a mathematical tool, to break down global data into its fundamental patterns.
So instead of treating Earth as a flat grid, it acknowledges its true shape.
Yeah.
Makes sense, because Earth's curvature and rotation, they hugely impact climate patterns, right?
Absolutely. SFNO captures these effects much better than models that might just treat Earth as flat.
So spherical DYffusion uses SFNO to understand and predict how the climate evolves over time on a spherical Earth, and DYffusion provides the framework for generating these multiple possible futures.
You got it. It's a powerful combination that allows spherical DYffusion to create these realistic, physically consistent simulations of the Earth's climate. And get this, it does it much, much faster.
Speed, the holy grail of climate modeling. I mean, those simulations are notoriously resource-intensive, even for supercomputers.
You said it. And the paper breaks down the computational complexity, comparing spherical DYffusion to other methods. It's significantly more efficient, even compared to fast deterministic models like ACE.
So not only is it fast, it's also more accessible, potentially. This could be huge for climate research, allowing more scientists and institutions to get involved.
Democratizing climate science, I like that. But how did they actually train this spherical DYffusion? What data did they use?
Right, got to teach you somehow.
They trained it on 100 years of simulations from a sophisticated physics-based climate model called FV3GFS, Finite Volume Cubed Sphere Global Forecast System, if you want the full name.
Catchy. So it's learning from a master climate model, absorbing all those complex relationships between different climate variables.
Precisely. And to avoid just memorizing the data, they tested it on a separate 10-year simulation, seeing how well it generalizes to new climate conditions.
How to do? Pass or fail?
It passed with flying colors. Spherical DYffusion significantly outperformed other ML models, even some simplified physics-based ones. It came amazingly close to the original FV3GFS model's performance, but at a fraction of the computational cost.
Talk about efficiency. So these climate simulations are faster than traditional methods while still being very accurate.
That's amazing. That's the goal, and the early results are really encouraging. But remember, we're not just aiming for any simulation. We want accurate representation of the long-term average climate. And even small errors over long periods can lead to significant biases in our projections.
Right, those biases are a big concern in climate modeling. So how did spherical DYffusion fare in that regard?
Well, this is where it gets exciting. Spherical DYffusion showed significantly lower climate biases compared to other methods, especially for key variables like total water path, which measures atmospheric water vapor.
Okay, total water path. Got it. And what did the results show?
They actually visualized the biases in the paper, and spherical DYffusion's bias for total water path was so small it was almost indistinguishable from the natural variations in the reference simulations.
Wow, so it's capturing not just the climate, but the natural randomness of the system itself. Pretty impressive. But hold on, we've been talking about how it learns from FV3GFS, this base climate model. Doesn't that mean it could inherit any biases that already exist in that model?
No. That's a sharp observation, and you're right, the researchers acknowledge this. For spherical DYffusion to truly shine, we need to tackle those biases in the base models themselves.
So how do we debug our climate models, so to speak? Get rid of those pesky biases.
They suggest incorporating insights from even more detailed models, like global storm resolving models, which capture finer scale climate processes that traditional models miss. It's like using a higher resolution camera to see the fine details.
So by feeding spherical DYffusion with info from these more precise models, we could potentially mitigate those biases.
Exactly. It's like giving our student multiple teachers, each with unique expertise, for a more well-rounded understanding of the climate system. Yeah, it's like you said, if your cooking teacher always oversalts, you'll probably end up doing the same. We need to fix those base model issues.
So how do we desalt these climate models? Where do we even begin?
Well, the paper suggests using insights from those super detailed models. Think global storm resolving models. They can capture the tiny climate processes that regular models might miss.
Like using a high-res camera to catch those subtle details.
Exactly. Give spherical DYffusion info from the sharper models, and we might just smooth out those biases.
Okay, so multiple teachers for our AI student. Got it. But besides those biases, what else stood out to you about how spherical DYffusion performed?
They looked at something called climate variability, and that impressed me.
Climate variability. Remind me what that means again.
It's how much the climate naturally fluctuates over time. You know, even without things like greenhouse gases, the Earth's climate isn't constant. It warms, it cools, there are droughts and floods, all happening over years, decades, even centuries.
Right, like those El Nino and La Nina cycles we always hear about.
Yeah, exactly. And what's cool is that spherical DYffusion could accurately recreate this variability. They compared its simulations to those 10 independent FE3GFS simulations, you know, the base model and the variability in spherical DYffusion's results, matched the reference simulations almost perfectly.
So it's not just mimicking the average climate, it's getting those natural fluctuations too. That's pretty important for understanding how this whole climate system works, right?
Absolutely. Shows us that spherical DYffusion is really learning the underlying dynamics, not just memorizing patterns. It gets it.
They ran a lot of tests on this model, didn't they? Anything else jump out at you?
Well, they did this 100-year simulation, a whole century. Really put that long-term stability to the test.
Wow, a whole century. That's a long time.
It is, and throughout that entire simulation, it stayed stable, produced realistic patterns responding to the annual cycles of sea surface temperature and solar radiation. It's the real deal.
That's wild. But going back to efficiency for a second, those long-term simulations would take forever with traditional climate models, right?
Oh, absolutely. Traditional models, they're slow. But spherical DYffusion, because it uses machine learning, gets similar results way faster. It's a game changer, honestly.
So we could run more scenarios, get faster results, potentially make better decisions about how to deal with climate change.
Yeah.
All thanks to speed.
You got it. And it's not just about speed, it's about accessibility. Faster, more efficient models could mean more researchers and policymakers, even those without supercomputers, can get involved.
So we're democratizing climate science, but on a technical level too. Very cool. But how does it actually work under the hood? Break it down for me like I'm a machine learning expert, but maybe a bit rusty on the specifics.
All right, let's do it. So, imagine today's weather. We want to predict a few steps ahead. Now, DYffusion, it takes a roundabout route. Instead of just predicting, it imagines the weather getting more and more random, like adding static to a radio signal.
Intentionally messing up the data. Sounds counterintuitive.
It is, but it works. Then DYffusion trains a machine learning model to reverse that process, to denoise the weather and find the actual future conditions.
So it makes a mess, then cleans it up, and somehow that teaches it to predict the weather. Interesting approach.
Exactly. By undoing that artificial randomization, the model learns the real patterns of weather evolution. But we need to add in SFNO, and that's where things get really interesting.
Okay, SFNO, the spherical part. Let's hear it.
It's all about understanding the Earth as a sphere, not just a flat map. Think of trying to wrap a basketball with a flat piece of paper. You need curved shapes to match, right? SFNO does that with data using something called a spherical harmonic transform. Breaks the data down into curved patterns that fit perfectly on a round planet.
Ah, so instead of forcing the Earth onto a flat grid, SFNO lets the model see the Earth as it really is. Makes sense. The Earth's curve, its rotation, those impact weather and climate massively, right?
Big time. SFNO handles those effects way better than models that pretend Earth is flat.
So DYffusion, our weather detective, gets paired with SFNO, who knows all about the Earth's shape, like giving our detectives special 3D glasses.
That's the idea. Combine those powers and you get spherical DYffusion. Fast, accurate, and physically consistent climate simulations all on a spherical Earth. Pretty neat, huh?
Super neat. But how does it generate those multiple possible futures we talked about, those ensemble simulations, I think they were called?
Ugh. That's where diffusion models really shine. Remember how DYffusion adds noise to the weather data? It doesn't do it just once, it does it multiple times, creating a bunch of noisy starting points.
So instead of one blurry picture, we have a whole stack of them, each blurred a bit differently.
Bingo. And the model learns to denoise each blurry picture, essentially creating multiple paths the weather could take from that starting point. Like, what if it rains tomorrow, or what if it's sunny? It explores those what-ifs.
So each denoised picture is a possible future weather scenario. That's pretty cool.
It is. And by creating a whole bunch of these simulations, we get a much better understanding of the range of possible climate outcomes. Instead of just one prediction for tomorrow's temperature, you get a range, showing you the uncertainty involved.
It's like a weather forecast with options, acknowledging that the climate is a complex thing.
Exactly. That ability to generate ensemble simulations is a huge plus for spherical DYffusion. We can explore not just the most likely future, but all the potential outcomes. That's key for making smart decisions about climate change.
This has been a fascinating look at spherical DYffusion. We've seen how it uses DYffusion and SFNO to tackle some of the big climate modeling challenges, but I feel like there's more to uncover.
There's always more. In our next segment, we'll look at the potential implications of this model and what it could mean for the future of climate science itself. Stay tuned.
Okay, final part of our spherical DYffusion deep dive. We see how it works, its strengths, and some hurdles. But let's zoom out now. Look at the bigger picture.
It's a cool technique, but where does it fit in the whole world of climate modeling? What could it mean for the future of climate science itself? That's what I'm thinking about.
Exactly. Less technical details, more big picture stuff. What are the researchers hoping to do with spherical DYffusion ultimately?
They see it as this powerful tool for tackling some of the biggest questions we have in climate science. Like, a huge challenge is figuring out how climate change will impact different regions of the world, right?
Because it's not just about the global average temperature going up. It's about how that affects different places specifically. Some might get more heat waves, others more rain or drought.
Exactly. And spherical DYffusion, since it's so fast and accurate, could be amazing for regional climate modeling. We could project how climate change will affect specific areas, helping people prepare for what's coming.
So instead of a blurry future, we get a clearer picture of how things might change locally.
That's the goal. That kind of regional detail could help with everything from planning infrastructure to agriculture to disaster preparedness. Super important stuff.
Like a crystal ball, but for local climates. No more just general trends.
And that local info is key for making good decisions about adapting to climate change. It's not enough to know sea levels are rising globally. Coastal towns need to know how much to expect in their specific spot and how that might affect them.
So spherical DYffusion could help communities take action based on real science, not just guesswork. That's powerful. But aside from regional stuff, are there other uses for this model?
Oh, tons. The researchers think it could be used for all sorts of climate science investigations, like studying the impacts of different greenhouse gas scenarios. What if we keep polluting versus what if we cut emissions drastically?
We could run those scenarios through spherical DYffusion and see how they affect global and regional climates, like a choose-your-own-adventure for the planet.
Exactly. We could explore way more possibilities and really grasp the consequences of our actions. Important stuff for policymakers dealing with climate change mitigation.
This all makes me think about machine learning's role in climate science as a whole. It seems like spherical DYffusion is just one example of how ML is changing the game.
You're right, it's happening all over. Weather forecasting, climate modeling, analyzing huge data sets. Machine learning is everywhere.
A brand new tool in the climate scientist's toolkit.
And it's a good one. Machine learning algorithms are great at spotting patterns and connections in complex data, which is perfect for climate science.
So as we get more and more data about the climate, ML helps us understand it all, find those hidden insights.
Exactly. This could lead to huge breakthroughs in how we see the climate, how we see it changing. It's exciting.
With all this progress, what do you think the future holds for spherical DYffusion specifically? Any guesses?
Well, the researchers are already working on some cool stuff. They want to add other parts of the Earth system to the model, like oceans, land, ice sheets, the whole shebang.
Right, we've mostly focused on the atmosphere, but the climate is way more complex than that. Everything's connected.
Exactly. So they want to link spherical DYffusion with models of those other parts, create a truly comprehensive Earth system model. Ambitious, but powerful.
A virtual Earth in a computer, simulating the entire planet. That's mind-blowing.
It is, and spherical DYffusion could be a big part of making that happen.
This whole deep dive has been amazing. Spherical DYffusion really shows how machine learning can revolutionize climate science and help us tackle climate change head-on. Really inspiring stuff.
Totally. And remember, this is just the start. AI-powered climate modeling is booming, so expect even more incredible stuff in the coming years. The future's bright, and we're just getting started.
So to all you ML experts out there listening, this field needs you. Your skills are crucial for tackling these complex climate challenges. Get involved.
We've only just begun to see what's possible.
Oh, yeah.
Keep learning, keep innovating, keep pushing those boundaries. The planet needs your help.
This deep dive might be over, but the conversation continues. We hope you've enjoyed learning about spherical DYffusion, and we encourage you to keep digging, keep questioning, and keep exploring the awesome world of climate science. There's always more to discover.
Thanks for joining us. It's been fun.
Until next time, stay curious.